All right, I'm going to go ahead and get started. It looks like we're missing most of the class, but we're not going to have a full session today. I'm going to lecture for maybe an hour or so, and then I did put up, I don't know if you noticed or not, I put up your first lab. Lab 1 doesn't require any equipment. It's more calculation. So I put that up. So what I would recommend, since we're going to have a short lecture today, that you might want to print that lab out and start working on that. And I don't have a due date on it yet. I'll give you a due date later on, but you definitely can use some of this time to do that and use it to your advantage. The other thing is I did make a video. I don't know if you had a chance to watch it or not. I made a video of that packet that I referred you to on Blackboard. And in there, in the video, I talk about the power distribution system so you can kind of see what I was saying. And I go over this a little bit, the generator and how they kind of figured out that the force acts in the sinusoidal way. So I kind of try to go through that. So hopefully with the last lecture, the video I made of the packet, and this review, hopefully it makes sense to you. So I want to go back to that. Just kind of as an overview or review, last time we were together, we talked about ways to create AC. How can I make an AC waveform or AC voltage or current? We talked about different ways, but this idea of rotating machine, something that moves in a circle, we talked about that and spent quite a bit of time. So when I have these machines that rotate, we call it a generator. And I think on the handout there was a big generator station, and there was a portable generator. And I asked, well, what do these have in common? The thing that they have in common, I think it was Jacob that mentioned, they have a rotating shaft. And you can see now why we have that rotation, why the rotation is necessary. Based on Faraday's law, if I want to induce a voltage, I got a magnetic field, I got to have a current, I got to have motion. So the kind of motion, the linear motion back and forth, I can actually induce a voltage across a wire, but that's not very practical. So to set it up to where that coil rotates in the magnetic field is much more practical, and it's easier to design a generator based on that kind of motion. And so we have the rotating machines. So what I tried to do in the last lecture was to go through and show you by the different positions of the coil in the magnetic field how much voltage is being produced. And I tried to kind of walk through that, and I'll kind of do it again today. One of the things I did, though, I said, let's take an arrow and attach it to the coil. So I put a little arrow right here, like this, and just attach it to the coil. And what happens now, as that coil spins, the arrow is going to spin along with the coil. They might say, well, why would you want to do that? Well, the reason we want to do that is I want to abstract from the machine. I want to get away from the machine and just deal with concepts. We want to deal with the mathematical concept. And so by doing this arrow thing, what I can do is I can draw that arrow over here. I can take a coordinate system and I can draw the arrow over here like that. And that arrow shows the position of this coil as it rotates around 360 degrees, and then it keeps repeating. And then I hope I mentioned that when you take an arrow and you attach the tail of the arrow to the origin of a coordinate system, we call that thing a phasor. Some of you might know a vector. You've probably seen or heard of a vector. So there are vectors, and then there are phasors. So they're kind of similar to each other in that both of these things, we use arrows to represent vectors, and we use arrows to represent phasors. Now, a vector is just an arrow whose magnitude is equivalent to its length. So if that's vector A, a vector 2A would be twice as long as that, but it has the same direction, the same orientation. So if you're familiar with vectors, phasors are kind of like that. But the difference is, a vector, I can take a vector, and as long as I don't change the length of it or tilt it, I can move it anywhere I want in space, and it's the same vector. So I can move a vector around in space, whereas when I take that vector and attach it to a coordinate system and it spins around, we call the phasor now. Phasors don't move in space. Phasors move in time. So it's a kind of a little hard conceptual idea to get your mind wrapped around, but just suffice it to say, phasors and vectors are related. I can move vectors around in space, phasors move around in time. But just to keep it easy, you're really going to have to think about it like that. An easy way to think about it is, I just want to keep track of where that coil is as it goes around its journey, 360 degrees, and it keeps repeating. And so I'm going to put an arrow on there, and that arrow I'm going to represent on this XY coordinate system. So when that coil is flat, then that arrow is at 0 degrees. As it goes around, the coil gets up to 90 degrees where it is now, and that arrow is pointing straight up. And when it goes over to quadrant 2, the arrow over here is in quadrant 2. So this right here follows this. Now, why would you want to do that? Well, we know because of Faraday's law that as this coil spins around in the magnetic field, it's generating forces. Remember what we said, the right-hand rule shows you that there's always a force on the charge moving through a magnetic field. The question is, how would you describe that force mathematically? Is it linear? Is it a quadratic? What is it? Is it x cubed? What does it look like if you make a mathematical model of it? What math function describes that force? So how do you figure that out? And that's when we went and we said, all right, let me take a light beam, a beam of light, and I don't know who figured this out, but somebody thought about, let's take a beam of light and shine it this way. And if I do that, then what I can do is I can watch the shadow of the phasor. When that phasor is down like this, if I put a screen, piece of paper, like a movie screen right here, if I put a screen right there, what I would see, if the phasor is right here at 0, which represents this thing being at 0 degrees or position 1 in that handout, then what I would see is a dot. The shadow would look like a dot. But as this starts to move up, it's in the position where it is now, then the shadow is now like this. And as it gets closer to 90 degrees, at 90 degrees, the shadow and the actual phasor are the same length. So eventually from 0 to 90, what you get is this. And then over here, when the phasor is over here, now I got to move the light source over here so it's shining back this way. But now instead of growing, the shadow is shrinking. So what you get, if you plot this all the way around 360 degrees, if you plot the shadow of this thing, what you get is a diagram like this. Here's at 90 degrees where that shadow is maximum, the same height as the phasor. Now over here we're in quadrant 2, so the shadow is starting to shrink. And right here, the phasor is actually pointing this way at 90 degrees or 180 degrees, so it's a dot again. And now we're down, we moved to quadrant 3, so my shadow is now pointing down. We're at 270 degrees, so we're here. When I get to quadrant 4, now it's shrinking again. And when I get back where I started from, I get the dot again. So this diagram, really what we're diagramming here is the way the forces are acting on the conductors in the wire. And remember, it's the force that separates the charge, so it's the force that makes the voltage. And it's the voltage that makes the current. So if the force is behaving this way, then the separation of charge or the voltage has the same exact graph. And the current created by that voltage has the same exact graph. So if you connect the dots, what do you have? Well, like we said before, you have a sine wave. So no, the force on this is not linear. No, the force is not quadratic. It's not an x cube. It's none of that. You can see it obeys, it follows this. That's a sine wave. So we know about that. That's kind of nice when we have nature behaving like something we already know about. Mathematicians already know about sine waves. So you've seen this in your trig class. Y equals sine theta. Where theta is this angle right here between the positive x-axis and where the position where the phasor is. So what we want to do is, I like to predict the voltage I would get out of that machine. I know, based on Faraday's law, I can get voltage out, but what does the voltage look like? Well, now we know it's a sine wave. Why does it look that way? Well, it's not linear, it's just the way this thing turns in the magnetic field. it provides forces, provides a voltage, which provides a current sinusoidal. And so that's nice. So basically I can do this. I can write that the voltage coming out of this thing, I don't want to use my Y, I'm going to use a V for voltage. And notice the way I draw that V. I didn't draw it like this. That's going to have a different meaning. I drew a lowercase script v. So for us, v is going to equal sine of theta. The voltage coming out of this thing is going to equal sine theta. Let's see if that we think about that. Does that really work though? If you think about it, if you take the sine of 0 degrees, you get a 0. So at 0 degrees, we expect the voltage to be 0, and that's reflected here. At 90, we expect it to be a maximum. Now, if we take the sine of 90 degrees, what you're going to get is a 1. Matter of fact, if you think about it, the biggest, if I use this equation, the biggest value I can get out here for y or for v is 1. If you remember the sine function from your trig class, the sine varies, it alternates between positive 1 and negative 1. So as if I show this way, this sine wave has an amplitude is the word. It has a height, an amplitude of 1, a negative 1. It alternates between 1 and negative 1. So as long as I have a generator where I have 1 volt between positive 1 and negative 1 volts, this will work. The problem is a generator that puts out 1 volt is pretty useless. So that doesn't work. So here's what we can do, or here's what's done. Instead of writing the expression for this like that, I'm going to write it like this. I'm going to put that factor of A in there. So now I'm taking A max times sine. You can think of this as the amplitude. That's called the amplitude. So here's what happens. The sine itself varies. The highest the sine can be, the sine function, the highest it can be is +1, and the lowest it can be is -1. From trigonometry, you should know, from your algebra and trig class, you should know that a sine function varies between 1 and -1. And so the highest this can be is 1, the lowest this could be is -1. But see, if I put this factor in there, I can make this output be anything I want. For example, I can say, all right, I'm going to let A max, the amplitude, equal 10. If I let that equal 10, then I can rewrite the equation like this. I can say y equals, we'll let A max equal 10 sine theta. And now what happens, this part of this expression, the highest it can get is 1, the lowest it can get is -1. But whatever this is, I'm multiplying it by 10. So when the sine wave is at its highest point, 1, I multiply that 1 times 10, and my output over here will be 10. When the sine swings to the lowest point, which is -1, I got -1 times 10, and my output over here is -10. So now the sine function oscillates between 1 and -1, but the actual output oscillates between 10 and -10. So this is how we're going to get around this. When I write this for voltage, if I put this amplitude in there, they're not going to have this could represent a generator that puts out any voltage. So here's how it's going to look for us. An AC waveform. In math, I use X, A, and sine, but in engineering, for electronics, over here, for the output, we're going to use a V for volts. So instead of using Y and A and all of that, our equation is going to look like this. It's going to be V equals, now instead of A for amplitude, we're going to use a VP sine theta. So this is going to represent the voltage coming out that generator. So let me clean this up a little bit and we'll talk about it. V script is VP sine theta. So here is the expression that we will use for AC. This right here, that script V, is called the instantaneous voltage. Why is it called the instantaneous voltage? Because if this is my waveform, if this is voltage, then think of this as time. You tell me to look at it, what instance in time to look at it, I'll tell you what the voltage is. Right here, the voltage is 0. Right here, the voltage is some maximum value. So this voltage over here is an instantaneous voltage. You got to tell me at what angle or what time to look at it, and I'll tell you what the voltage is at that particular time or that particular angle. So that's the instantaneous voltage. This is called the peak voltage. It's also called the amplitude. The amplitude. Now, in some books, instead of VP, instead of using VP, some books are using VM. That stands for Vmax. Either one is okay. That stands for V peak. So either VP or Vmax is what you'll see right here. And this right here, that angle, that's the angle the coil is making with respect to the positive x-axis. If you think of this xy coordinate system, that angle theta is right here. So this is pretty important. This is the formula we're going to use for AC voltage or current. Instantaneous value, the amplitude or peak value, and then the angle. So, for example, I might give you a voltage that looks like this. I might tell you, I might give you a waveform and say that waveform is 100 sine theta. And then what you can tell me is, okay, I know the amplitude or the peak voltage. The maximum voltage that can come out of that generator is 100 volts. That's what that is. That's the peak value. You can also tell me the voltage at instant in time or any angle. If you tell me where the generator coil is as it rotates around the 360 degrees, I can put that angle in there and tell you what the voltage would be at that point. So that's how you work with that equation. But we need more information. This is not good enough. I want an equation to give me even more information. So let me go back to this phasor idea. Here's what I have. I got my phasor. And that phasor is rotating. Now, it's customary when we have a phasor, this phasor rotates counterclockwise. It's just kind of a convention. So when we talk about phasors, we usually let them rotate counter. There's a reason for it, but it's more of a mathematical thing. So we always think of phasors as rotating counterclockwise. So remember, this phasor is telling us where this coil is. That arrow right there telling us where the coil is as it goes through its journey around 360 degrees. So that phasor is rotating. Now I want you to think about something. This theta right there, that angle is right here. That's that angle, this theta. I want you to imagine if I, at the tip of this, at the very tip of that, let's say there was a firefly or a lightning bug. I don't know what you call them, the little lightning bugs, or a little light right there. If there was a lightning bug or firefly right there, and you turn the light out, and it's dark, and this thing is rotating, what would what you see? Well, clearly what you would see is you see the light make a circle. This would make a circle. And if I just let this thing spin freely around, if there was a little light at the tip of that, you would just see a circle of light. Well, that's kind of nice because if you think about it, here's what you can do if you wanted to. You could actually tell how fast that phaser is rotating, which is telling you how fast that coil is rotating, if you do this. What you would need to do is to get a starting point for the phaser. Let's say it started here. I call that standard position. So let's say the phaser moved from this point all the way up to this point. Well, if I had a stopwatch and I start right here, and once I let that phaser spin, I stop it. Let's say I stopped it right here. So maybe this is my initial time, and this right here is my final time. What I can do is I can measure this length right here. I can measure that length or that distance. If I measure that distance divided by the time it took to go from here to here, divided by the time, then what I get is the speed or the velocity of the phaser as it spins around. I can measure that actually on the graph. So there's some information I can get. I'm going to use well, I don't want you to confuse this V for that V. But I'll make this V a little bit bigger. So this is V. So I'm trying to see what kind of information can I get out of this diagram that might help me mathematically. And I can experiment with this. And this is one of the things I can do. I can figure out how fast this thing is turning. Now, I don't know if that's going to do me any good or not, but hey, I can figure it out and see if I can use that information for something. So I can do that if I get the starting point and the ending point, and I know how far it goes between the starting point and ending point, then I can just take the final time minus the initial time to get this delta t, which is right here. I'll put a delta t there for you. And if I measure this distance right here, if I take the distance divided by the time, you get the speed or the velocity. But this is called the linear velocity. I don't know if you can see if there's a light shining up there. This velocity, doing it this way, is called the linear velocity. And the reason it's called the linear velocity, you might think linear, straight line. There's a straight line here. This thing is moving in a circle. Why would I call it the linear velocity? The reason it's called the linear velocity is that really at any particular position, the thing is actually moving in a straight line. So what I'm saying is, at this position right here, the velocity is like this. It's following that line right there. But when the phaser moves over here, then it's following this line right here. If you think about it, let's say I had a pole. If I had a pole with a string on it tied to a rock, and I make it spin around, and you're looking down at it. So you're looking down. Here's the top of here's the tip of the pole, and I got a string coming out like this. And here's my rock, and that rock is just going around the circle. If somebody cut that string at this point right here, that rock is going to continue to go in the straight line. It's not going to continue to go in the circle. The only reason it's going in the circle is because the string is pushing toward the center. That's called a centrifugal force. But if I were to cut that, it'll go in a straight line because at every position of the circle, the thing is really moving in a straight line. And so that's why they call this a linear velocity. It's just straight line velocity at any point, even though the overall trajectory, it looks like it's moving in a circle. So that's one of the things we can do. But unfortunately, this doesn't do us much good with what we want to do in this class. But if you think about it, not only is the distance changing with time, there's something else up here changing with time that will do us some good. And I want to show you that. But let me clean this diagram up. Let me redo this. I redraw this, and I put my phaser in there, and that phaser is going around the circle 360 degrees. So the light is making this circle like that. And we said that this angle right here, when we measure the position of it, then this angle tells us the position of the phaser, which is telling us the position of the coil. And I already showed you that this distance right here between some starting point and ending point is changing with time. So if I get the time it takes to go this distance, and I divide that distance by the time, that gives me velocity. It gives me a linear velocity. V equals d over d, linear velocity. But something else up here is changing with time. And the thing that's changing with time is that angle. That angle is getting bigger with time. And so just like I can take this distance, d, and divide by time, I can do the same thing with the angle. I can take the angular distance and divide by time. And if I do that, if I take the angular distance and divide that by time, then what I get is something called the angular velocity. If I take the linear distance and divide by time, I get the linear velocity. If I take the angular distance and divide by time, I get the angular velocity. And so as a formula, let me show you what that would look like. For linear velocity, they use a V. For angular velocity, they use this Greek letter omega. Looks like a W with the sides bent. So this angular velocity is the angle divided by time. So I can do distance divided by time. Maybe this is so many meters per second. Or I can do the angle divided by time. Now, when we do an angle divided by time, you know you can measure angles. Usually they're measured in degrees or radians. Well, anytime we use this method, this will always be in radians. So this is in radians. We'll say rads. And time is always in seconds. So the angular velocity has units of radians per second. Radians per second. So think about this now. I said we can take voltage. We can represent it like this. If I know the peak value of my generator, if I know the amplitude, you tell me what angle you want me to look at it. You tell me the position you want me to look at the angle or the coil, and I'll tell you what the voltage is at that angular position. And so that theta there is that theta. Well, if that theta is that theta, look at what I can do. If I wanted to, I can actually solve this equation for theta. Let's solve it for theta. If I solve it for theta, what I get, multiply both sides by t, I get theta is equal to omega t. Theta is equal to omega t, the angular velocity times time. This theta is that theta, so what that means is I can substitute omega t for theta. So right here, instead of having theta there, I can actually write omega t. Now that's kind of nice right there, because if I'm designing a generator, now I'm relating a generator, the voltage out, to how fast it's rotating. If I can design it to go a certain number of radians per second, or if you wanted to, you can convert radians per second to revolutions per minute. Usually a revolution per minute, RPM, is how engineers design things that spin. But now I'm relating the voltage to basically speed, an angular speed, but a speed. So that's kind of nice. So what would this look like? Well, it might look like this. I might give you an expression that says that this generator is 100 sine 377t. 100 sine 77t. So what if I gave you that? What information can you get from it? Well, right here, that would be the peak voltage. Right here in front of the T, that's that. What is that? Well, that 377 would be the angular velocity. That would be omega. Omega equals 377. The units would be radians per second. So now I can just look at this and tell how fast the generator coil is moving if I wanted to. Remember, that's radians per second, but with a little bit of math, you can convert radians per second to revolutions per minute or revolutions per second, whatever you want. So this way of writing an AC waveform gives me even more information, but you got to be careful. Now look at what I'm doing here. If you're actually going to use this in your calculator, you got to be careful because look at this is called the argument right here. This part right here, the argument. So let's look at that argument, and I want to show you something. What you're doing is, this is omega. You got omega, which is 377. So that's omega. And I'm taking omega and I'm dividing by t. Or multiplying by t. So I'm multiplying this by t. Well, if you multiply omega times t, I multiply omega times t. If I multiply both sides of this by t, what we have is omega's in radians per second, right? That's in radians per second. And that t will always be in seconds. So if I multiply this by seconds, I take radians per second, multiply by seconds, and I get radians. Now you got to follow what I just did. That's showing you that the argument here, I'm taking radians per second and multiplying by second. The thing in the argument is radians. So when you do a calculation with this, you got to change your calculator to radians because the argument is in radians. And so the way we're going to represent an AC waveform is more like this. So it gets more interesting as we go. Well, I want to introduce you to a couple more terms, AC terms. Two more. I want to introduce you to one term. It's called the period. And then the other term is called frequency. What is the meaning of period and what is the meaning of frequency? So let's look at that. The period of a waveform. I want to relate this to a circle. So you now know that if I take that phasor and let it rotate, it's going to rotate counterclockwise. It's going to rotate in the circle. Well, if I start this at 0 degrees, let's say I start at 0. So I start my phasor at 0. As it goes around from here to here, what it's doing as far as the sine wave is concerned is that's the first quarter cycle of the sine wave. As it moves from here to here, that's the other half of the sine wave. As this phasor now is in quadrant 3, that's this part of the sine wave. And when it moves to quadrant 4, then it finishes out the sine wave. If you looked at that when you had that shadow projection thing that I told you about. So every time this goes around one time, it produces a sine wave. So we call this a cycle. This is called a cycle. And when this spins around, this is called a revolution. I just call it a rev. So here, one revolution causes us to have one cycle. One revolution of the circle is one cycle of a sine wave for voltage, current, or force. One revolution of the circle gives us one cycle of the sine wave. So the period is how long does it take for one cycle? How long does it take for one of these? How long? So the period, now for period, you might think we use a P, but we use a T. That capital T like that, we use that for period. So the period is the time, the T-I-M-E, the time for one cycle. The period is the time for one cycle. So how long does it take to go from here to here? Is equivalent to the amount of time it takes to go around the circle one time. So you want to remember the period is the time for one cycle. The frequency, if you think about it, what's happening, say this is your eyeball right here. You're looking at this phaser spin around and around and around. If you count how many times it goes past your eyeball, how many times you see it, how frequently does it go by, that's what you mean by frequency. But it's a little bit more than that. Because when we look at frequency, I have this thing called a time space. Let me put that on the board. A time space. Time space. What a time space is, instead of looking at an object and say a fixed distance, let's look at something in a fixed time. So my time space is going to be 1 second. So from here to here, let's say that represents a time space of 1 second. 1 second. From there to there. The frequency is how many of these cycles will fit in a space of 1 second. So if I'm in my time space here, let's say I have a waveform like this. That frequency is 1 cycle per second. If I have something like this, then I have a cycle here, and then I have another one there. That frequency is 2 cycles per second. So the more of these things I have in there, I might have something like this. That's a lot of cycles per second. So time space, I want to see how many cycles appear in 1 second. That's how we think about frequency. Now, this cycle per second is actually a unit. And what they do is they say that 1 cycle per second, we call that 1 hertz. And instead of writing the word hertz, is capital HZ, because Hertz is the person's last name. This was named after somebody. So in other words, if I say, hey, that waveform has a frequency of 100 hertz, that means you have 100 cycles in that time space of 1 second. If I say the frequency is 1 kilohertz, a kilo is 1,000, that means there's 1,000 full cycles in that time space of 1 second. Now remember, each waveform, each one of these comes from 1 revolution of the circle. So if I have 1,000, well, let's say 100. If I have 100 cycles per second, That means this thing has went around the circle 100 times in 1 second. So remember, equate one sine wave, one cycle, with one revolution around the circle. And basically, the number of revolutions around the circle is giving us the frequency. So the idea of the frequency, how many cycles per second, and the period, how long does it take for one cycle? And so I might give you something like this. So I got this waveform, and I give you some times here. And I draw a waveform like this. And it keeps going. And I tell you that these are seconds, right? I tell you these are seconds. Or it could be milliseconds, it could be whatever. So if I give you something like that, there's a relationship between period and frequency that you need to remember. And I'm going to give you the equation here right now. The frequency is equal to 1 over the period, or the period is equal to 1 over the frequency. Now, this is interesting because, remember, this thing right here is measured in seconds. So this will be 1 over seconds, which you can write like seconds to the minus 1. So remember I said the frequency is cycles per second? Frequency also has a unit of an inverse second. So an inverse second is also equal to a hertz. A hertz is equal to an inverse second. But going back to this, if this is my relationship for frequency and period, and this is my diagram, then what I can do, I can say, all right, well, the period of this waveform, that's the time it takes to go from here all the way over to where it starts to repeat. So this is in seconds. That's 1, 2, 3, 4 seconds. So my period is 4 seconds. If my period is 4 seconds, what's my frequency? My frequency is equal to 1 over the period, which is 1 over 4, which is 0.25. Now remember, this is in seconds. So it's 0.25, 1 over seconds. You write that as 0.25. Let me be neater with this. Zero 0.25, 1 over seconds. But 1 over seconds, the inverse second is a hertz. So you write that as 0.25 hertz. So that's a really, really, really slow frequency. So, but the point I was making is these formulas are important. So you want to start making a formula list, because in this class, there are a lot of formulas. Do I have any questions so far? I know we're doing a lot of math stuff here, but we haven't even started to use it yet. Anybody have any questions? Okay, well, let me show you one other thing. Let's go back to my mathematical model of an AC waveform, my formula. If I go back to that, what we said was that I can represent an AC waveform like this. And I can get information from this. This right here, that's the instantaneous voltage. You tell me what time t to look at it, I'll tell you what the voltage is at that time. This right here, that's the peak voltage or amplitude. I can look at that number and tell you the maximum amount of voltage you get out of this generator. And this right here, that's the angular velocity. You tell me what that number is, I can tell you how fast that coil is rotating in the magnetic field, because that's telling me how fast the phasor is rotating on the coordinate system, and the phasor is in sync with, or it's telling me how fast the coil is turning in the magnetic field. So by looking at that, I can tell you the speed of the generator coil. But look at what else you can do. Let me show you something. There's one more thing we can do to get even more information out of this. If this is true right here, think about this. Remember we said that omega equals theta over t, right? Omega, we said the angular velocity, so the angular velocity equals the angular distance divided by the time. That's what that means. Well, what if I do this? What if I do this? If I put right here, if I get rid of that, now this t right here is like an x in an equation. That would be like your independent variable. You can put in any old value for t, for time, and I'll tell you what value of voltage corresponds to that t that you pick. But this t is a different t. That's not any old t, that's a specific t, the period of the waveform. So if I erase this t, I take out this t, and I put in this t. Let me make it a different color. See, I put in that big T. I put in the period. If I do that, what would this right here have to be and why? Can anybody answer that? If I say that T, if I set this equal to the period in that equation, what does that have to be right there? What would that be? Anybody? What's the angular distance?
Zero? Is it zero?
Not zero. What is the period? What's the definition of the period? What do we say? The period is the time for what?
Is it 360?
It is 360. Do you guys follow where you got that from?
Yeah.
The period is the time for one revolution, right? Or one cycle. So if I make this time, instead of that t, if I make it that t, if I'm saying, hey, this is the period, then this angular distance has to be, it's got to be 360 degrees. The problem is we can't have that in degrees. So you got to remember from your trig, if I got from here to here, if this is 360 degrees, what would that be in radians? How many radians is that? Well, right here is pi radians. So this would be 2 pi radians. So you go around the circle, 2 pi radians. So if this is the period, then this angular distance has to be 360 degrees or 2 pi radians. That's got to be 2 pi. If I tell you that that's the period, then the angular distance has to be 2 pi. That's the circumference of the circle, or the distance around the circle. Now, if you look at this, and then look at that, you gotta pull this off a little bit. Let's say I do this. I get rid of that, and I write this like that as 1 over the period. That's exactly the same. You know, instead of doing that, I'm showing it, if I multiply that by that, I get this thing back. But by showing it this way, you can see clearly that this thing right here is really that, right? Frequency is 1 over period. So omega, following that logic, omega really is equal to 2 pi, and this thing right here is equal to f. So if I wanted to, I can take this and put it in there for omega. In other words, I can write this like this. I can say that my script V is V peak sine omega, but I know that omega is 2 pi f, that's omega, and I got to multiply that omega by t. You see it? So, you could do this. You guys, I need a calculator, so somebody get a calculator out for me real quick. Let's say I gave you this. I gave you this is 100 sine 377t. Let's look at what we can get out of this. Well, right here I can look at this and tell you my amplitude. My peak value, I can look at that. My peak value is 100 volts. So that generator can put out a maximum of 100 volts. What else can you tell me? Well, looking at that, that's this right here, that's omega, right? The thing in front of the T is always omega. So omega equals 377 radians per second. So now I can just look at that and tell you how fast the coil is moving in the generator. Now, usually you don't look at rotational speeds in radians per second. Usually you look at it in revolutions per minute. But you can take radians per second and convert that to revolutions per minute, just doing a little bit of math. So you can tell how fast the coil is rotating by just looking at that and doing some math. But not only that, look at this. Look at what else you can tell. Since I know that this right here is omega, and omega is equal to this right here is omega, then that means that omega is equal to 377 radians per second. But since omega is equal to 2 pi f, that's what we came up with. If I wanted to, I can solve this right here for f. F is going to equal omega divided by 2 pi radians. Right? So let's do that. If I take omega, which is 377 radians per second, 377 radians per second, I divide that by 2 pi radians, and here's where I need the calculator. I need somebody to take 377, divide that by 2, and then divide that by pi, and let me know what you get. Whoever has a calculator. 377.
I got 60.
Divided by 2. How much?
60.
60. You get 60. All right? You get 60. Look at my units though. I got I don't know what to erase. I got to erase this. So my units actually work out. On the top here, I got radians per second. Radians per second divided by, on the bottom, I got radians. radians. So if I do the math for that, I have radians per second divided by radians. That's radians per second times 1 over radians. That's going to go away. And what I'm going to get when I do that is 1 over seconds. Well, remember we said a frequency is inverse seconds? So this is 60, 1 over S, or 60 hertz. Does that number ring a bell for anybody? Frequency of 60 hertz, is that familiar to anybody? I think you know that the voltage on the AC wall outlet, most people know it's 120 volts. But the frequency is also 60 hertz. Did you know that? In the United States, it's 60. In Europe, it's 50 hertz. So that must mean that the generator coils down at Duke Energy, whoever's giving us our electricity, is rotating at 377 radians per second to give us a 60 hertz signal off the wall. One more thing we can get though. We got the voltage, we got the angular velocity, we got the frequency. If I got the frequency, then I can get the period. Pretty easy. When we get the period is just 1 over frequency. So I'll take 1 over 60. Now 60 hertz. Now here's where I want the seconds to come back. So it's going to be 60, 1 over seconds. What's 1 divided by 60? One divided by 60 is
Like 0.01666 repeating.
So I'm going to do this. There's going to be milliseconds. So there's the frequency, or there's the period. So it takes the generator coil down at Duke Energy about 17 milliseconds to go around one time. That is pretty daggone fast. We calculated all of that from this equation, and I didn't have to go down to Duke Energy to look at it at all. We did it all mathematically. Now, I know I did a lot in an hour because I think I have this session to set up to expire in an hour. Go back and rewatch this video, and we'll do some more of these calculations next class. I'll go through it a lot slower, but I just wanted to show you the equation we're going to work with is going to be more like this. Not like DC. We have a lot of things going on now, so our equation is going to be a little bit more complicated. Well, that's kind of what I want to do today. I want you guys to get online, go look at the lab I put up there, and you want to start working on that lab with the time that you have. Does anybody have any questions for me?
Yeah, I got a quick question. It's Randy, by the way.
Okay.
Yeah, are we gonna turn in the Tesla thing this week too? Or are you gonna put something up so that we can put in that the quiz that you had posted?
What did I tell you to do? Watch the test. What was the quiz about?
Yeah, watch the Tesla. Well, just watch the Tesla video and write a one-page report and send it in to you. You don't want us to email it to you, obviously. You're gonna put it on here, right?
Oh, you mean am I gonna have a way? Y'all have a way for you to upload it. You mean you went in the folder and saw the Tesla video? Y'all put a link in there. Did I put a due date on it? It shouldn't have been a due date on it.
No, I don't see a due date from what I can tell, but I can double check.
So just go ahead and watch it, and within the next week or so, go ahead and get it out the way and get your free quiz grade. So if before things get busy, we're gonna get really busy, guys. I would say go ahead and do it, get it out the way while we got time on our side, because we got a lot of stuff to go through in 10 weeks. So yeah, I'll have what I'll do is have a thing you can upload it to me, and I'll read it. I'll put it up in a couple days.
Okay, just double check.
Yeah, if you get it done, say you get it done, and send me a text saying, hey, can you grade it? And that'll remind me to go ahead and put the link up so you can upload it. So if you got it done already, I'll be happy to read it.
Okay, sounds good.
Anybody else?
Yeah, I have a question. I'm
Sure.
kind of spacing on the math that we did here when we divided the 377 by 2 pi.
Right here?
Yeah, you had me do it in 2 steps. You said divide it by 2, and then divide that by pi.
Oh, okay. So what I told you to do, I told you to, I said take 377. Oh, let me get a different color. I said take 377, divide that by 2, and divide that by pi. That's the same thing as taking 377 divided by 2 times pi. You should get the same number. Try it like this and try it like this and see if you don't get the same number. That will work out the same.
When I did it in my calculator, when I did 377 divided by 2 pi, I got like 592.
Well, no. When you do, if you do it that,
Yeah, that's Jacob.
if you do it that way, you got to put parentheses around it. Try it again.
Divided by 2, and then it just multiplied that by pi.
Yeah.
I got it.
Okay. Yeah, just your parentheses. That's all. At least I know you're working, though. You guys are working the calculator while I'm doing this. So yeah. Anybody else have a question or comment? Well, you can see that things are starting to get a little bit deeper, so you want to make sure you keep up on stuff. I'm going to put homework 1 up. I don't know. It'll be the next day or 2. And there's going to be some of this stuff, working with this equation a little bit to give you some practice. So I'll put homework 1 up there. You already have the lab 1. That's going to keep you busy. You have the Tesla assignment, and I'll put homework 1 up there, which you're going to work with this equation. By the way, this equation is called time domain. Time domain. I'll explain more about that on Monday. So that's it, guys. Have a great rest of the day. If you have any more questions, you can send me a text. And if you need to do something on the board, I can always hook up the camera and we can work on the board to go over anything you want. But other than that, that's all I have. Please look at that lab and start working on that because there's a lot of problems in there to do. But you really need to get through that. If you go through that lab, you're going to be in a really, really good shape to understand what's coming in a week or 2. So try to go through that lab and use the time today that you have to do that. Guys, have a great rest of the day, and I will see you later.